Hi there, in this video we're going to prove all of the circle theorems. And we're just going to start our way at the top left and work our way down and across until we've proved them all. Let's start with this first one. Now this first one's rather easy to prove because it almost follows from definition, but what we will do is we will just formalise it into a proper proof. So let's label this triangle OAB. So we have that OA is a radius and OB is a radius. That means that OA is equal to OB, and that means that triangle OAB is isosceles, and that OAB is equal to ABO. And then that's the first one done. Okay, on to our second one. So the angle at the centre is double the angle at the edge. And now our general strategy for this one is going to be to split this into half into two isosceles triangles. And we will call this triangle, or this angle A, and we'll call this angle B. And because they're isosceles, then I know that this angle here is also A, and I know that this angle here is also B. Let's just label up our triangle A, B, C. Okay, so now in triangle OAC, that's the top one, two of my angles are B, and that means I can work out what AOC is. So AOC, well, that's just equal to, if I wanted to work that out and we were given numbers, we'd do 180 minus these two angles. So that's what we'll do. We'll do 180 minus 2b. Okay, and then similarly for triangle OBC, we have angle COB, so that's this angle here, is 180 take away 2a. Okay, so we have this angle here is 180 minus 2a, and this angle here is 180 minus 2b. Okay, we're nearly there now. So we now have angle AOB to work out, so this angle here. Now that is the third of three angles around a point, and as we know, angles around a point add up to 360. So around O, we have AOB is equal to 360 minus AOC minus COB. I know AOC is 180 minus 2b, so let's substitute those values in. So minus 180 minus 2a minus 180 minus 2b. Now let's work this out. So 360 take away 180 take away 180. Well, they all just cancel. So we're left with negative minus 2a is plus 2a, and negative minus 2b is plus 2b. So that is AOB. And that's equal to, well, if I pull out a factor of 2, to a plus b. Now I know that a plus b is equal to ACB, this angle up here. So we can say that's equal to 2 times by ACB. Done. Okay, on to number 3. So two angles from the same point, or two angles from the same points on the circumference are equal. So what we'll do is we'll add in the centre and we'll connect our two lines here. So if this angle is x, and this angle here must be 2x. Now we're allowed to use that theorem because we've already proven it. Okay, so because this is x, this is 2x because of our angle at the edge is double the angle at the centre, And then for the same reason, I know that this angle here is also x, and because x equals x, those two angles are the same. And this is irrespective of where in this arc we draw those 2 points, it will always work. So that is our third one done. Okay, so on to number 4. So we're going to prove this one in 2 ways this time. The first way is we're going to apply the angle at the centre is double the angle at the edge once more. I know that this angle here is 180 degrees, and because the angle at the edge is half of that, I know that that must be 90 degrees. So that's one way we can prove it using this circle theorem. I'm also going to prove it where we don't use any circle theorems, we're just going to use, or we don't use this circle theorem, we use the fact that it's or we can form isosceles triangles. So let's split it like that. So if this here is x and this here is y, because this is isosceles, this angle here is also x and this angle here is also y. Now this angle plus this angle plus this angle add up to 180 degrees because they're angles in a triangle. So we get 180 is equal to y plus x plus this angle up here, which is x plus y. Okay, which simplifies to 2x plus 2y. Now if we halve the whole equation, we get 90 is equal to x plus y. And let's recall that x plus y is the value of this angle here. So we've just proven that that angle must be 90 degrees. If we're in a semicircle, it's a right angle triangle. Done. Okay, on to our fifth one, opposite angles in a cyclic quadrilateral. Again, we'll prove this in 2 ways. The first way, we'll use the angle at centre as double the angle at the edge. And the second way, we'll use nothing more than knowing that triangles are isosceles. So what we'll do is, we'll draw in our origin, we'll draw in a centre of the circle, and we will split it like that. So what we'll do is we will call this angle, well, we want to prove that these add up to 180. So I'm going to call this angle 2x, and I'm going to call this angle 2y, and you'll see why in 1 second. So because these are angles around a point, we know that 2x plus 2y is equal to 360. So that's around the origin O. Okay, so now what we're going to do is we're going to use our second circle theorem. The angle at the edge is half the angle at the centre. So if this angle here is 2y, well, that means that this angle here must be half of that, so that must just be y. Similarly, if this angle here is 2x, and this angle here has to be half of that, that has to be x. Now, from the angles around A, we know that 2x plus 2y is equal to 360. Let's divide both sides of this equation by 2. We get x plus y equals 180, but x plus y are just the opposite angles in this cyclic quadrilateral. So that proves it. We've shown that x plus y, or opposite angles, add up to 180. Okay, on to the second proof. Similar idea, except we don't need to use our other circle theorem. And what we're going to do this time, we're still going to draw our origin, but instead of splitting it into 2, we're going to split it into 4. And we will call this A, this B, this C, and this D. Now, because it is all of these triangles are isosceles, I know that this is also A, I know that this is also B, I know that this is also D, and I know that this is also C. Okay. Now, because we have 2 of the angles in a triangle, we can work out the third angle. So this angle here, well, angles in a triangle are up to 180. If we take away the 2 angles, we get 180 minus 2a. Similarly, we can define these other angles as 180 minus 2b, 180 minus 2d, and 180 minus 2c. 180 minus 2c, 180 minus 2d, and 180 minus 2b. Now if we add all of those angles together, we should get 360 because their angles are around a point. So let's do that. So 360 is equal to 180 minus 2a plus 180 minus 2b plus 180 minus 2c plus 180 minus 2d, which is, if we simplify that, 180 plus 180 plus 180 plus 180 is 720, and then we get minus 2a minus 2b minus 2c minus 2d. Okay, let's subtract 720 from both sides. We get minus 360 is equal to minus 2a minus 2b minus 2c minus 2d. And then let's divide both sides by negative 2. So that gives me 180 is equal to a plus b plus c plus d. And we'll notice that this a plus d is this, a plus b, sorry, is this angle. And this c plus d is this angle. So we've proven that the opposite angles in a cyclic quadrilateral add up to 180. Done. Okay, on to our next one. So this one, slightly different and slightly more interesting, because we need to prove that if a radius bisects a chord, then it meets at 90 degrees, and we need to prove that if a radius meets a chord at 90 degrees, then it bisects the chord. So two very subtly different proofs, but let's get to it. So our general strategy for both of these is going to be to split our triangle, or to form two triangles like that. Now I know that this green line and this green line have to be the same because they're both radii, and they share this red line, these two triangles. So we have that, and we've got two triangles where all three of the lengths are the same, so they must be congruent. And that doesn't quite prove that this angle is 90 degrees on its own. However, what we can do is, if we call that x, then because they're congruent, that also has to be x. But then because they lie on a straight line, those two x's have to add up to 180 degrees, which means that one of those x's has to be 90 degrees. So we've proven it in that direction. Now we'll use a similar thing here. So here we had side-side-side congruency, and down here we're going to have a slightly different type of congruency. Still going to be a similar method, it's going to be a slightly different congruency. So if that's 90 degrees, and that also has to be 90 degrees because they're on a straight line. Similarly, we have those lengths are the same because they're both radii, and this length is the same in both triangles. It's a shared side. So now what we're going to do is we're going to use right-hand side congruency to prove that that length is the same as that length, which means that it's bisected that chord. So that is sufficient for proof of this theorem, because we've done it both ways. So that one is now done. Okay, on to our next one. So we've got a circle, and we have a radius, and we have a tangent, and we want to show that the tangent meets the radius at 90 degrees. So this method of proof, if you go on to do A-level maths, this is called a proof by contradiction. So what we're going to do is we're going to assume that this angle here is at 90 degrees, and then we're going to see what happens. Hopefully we'll get something that doesn't work. So we'll show that if this is at 90 degrees, we get something that breaks down our understanding of maths. So the only way we can be consistent is if this is 90 degrees. Okay, so let's assume A is not equal to 90. Okay, well, if it's not equal to 90, then we can form an isosceles triangle with it. So if A is not equal to 90, then we can form an isosceles triangle where this is equal to A and this is equal to A. Remember, if A is equal to 90 degrees, we can't do that. But if A is not equal to 90 degrees, specifically if A is less than 90 degrees, we can form an isosceles triangle. Now, what we can do with that isosceles triangle is I know that one of these is the radius of the circle. If one of these is a radius of a circle, then I know the other one must also be the radius of a circle. So if we draw that on to illustrate what's happening. So because we can form this triangle with this tangent line, with A is less than 90, I've shown that my tangent must cross the circle at more than one point. So the tangent intersects twice. And because the tangent intersects twice, it's no longer a tangent. So the only way this can be a tangent and this can be a radius is if A is equal to 90 degrees. And the one thing we need to do be a little bit careful about is I only said if A is less than 90 degrees. If A is bigger than 90 degrees, well, we just take this angle, B, which if A is bigger than 90 degrees, B has to be less than 90 degrees, and we can use the same argument. So we've arrived at a contradiction. We assume that A was 90 degrees, or was not 90 degrees. We've shown that the tangent must intersect twice, so therefore the only thing that's possible is that A is 90 degrees. So this one is done. Okay, nearly there. So two tangents that meet at an exterior point have the same length. So what we'll do is we will add on our centre and we'll add on these two radii. Now from this theorem that we've just proven, we know that this is 90 degrees and we know that this is 90 degrees. And if we split or draw a line connecting the centre of our circle to the point at which they meet, well, that's a shared side, and I know that this length is the same as this length because it's a radius, and they're both right-angled triangles. So we have right angle, hypotenuse, side congruency. So the triangles are congruent, which means that this side and this side are also the same. So we've proven this one. And finally, onto the alternate segment theorem. So the alternate segment theorem uses a few of our other theorems to prove, but we can do it. So what we will do is we'll draw on the centre of our circle as often we have to, and we'll draw our perpendicular here. Of course, we know that that's 90 degrees, and we'll draw that on there too. Okay, so let's call this angle here x. Well, we know that this blue angle is 90 degrees minus x because the green angle is 90 degrees and this blue angle and this red angle exactly equal that green angle, so we get 90 minus x. Now these are two radii, so I know that this angle is also 90 minus x. And we're nearly there now. So we've got this triangle and we've got two of the angles in the triangle, which means we can work out this third angle. So let's work out that green angle. So to work out the green angle, we do 180 and we subtract the two other angles in the triangle. So we're going to take away 90 minus x, and we're going to take away the other 90 minus x, and that is equal to, let's call this, oh, well, we'll work out an expression for that in a second. That's our green angle. So 180 take away 90 is just equal to 0. And then take away negative x is x, take away another negative x, we get 2x. So this green angle here is equal to 2x. Now we can use our angle at edge is half the angle at the centre theorem to then show that this angle is equal to x, and there we have it, the alternate segment theorem. This angle x is equal to this angle x, which is what the alternate segment theorem states. So that one is done.